Alright, in this video we're going to develop the logistic growth model, and you guys can kind of look up here and read the narrative about where the differential equation for logistic growth comes from. Basically, it starts out like an exponential function, and then since growth tails off as the population increases or gets closer to the carrying capacity, we have this additional factor where we multiply. Whereas P gets close to the carrying capacity, this factor gets close to 0 and slows growth in the model. And so eventually we end up with this differential equation that dp dt is equal to kpe, which would just be the exponential model, times this slowing factor of 1 minus p over n. I don't want to get too much into that at this point in time. We're going to take this differential equation and turn it into the logistic growth model. So I've got dp dt is equal to k times p times the quantity 1 minus p over n. And from here I'm going to go ahead and distribute the p through the parentheses here to give us dp dt equals k times the quantity p minus p squared over n. And then I'm going to go ahead and find a common denominator for what's inside the parentheses. So we've got dp dt equals k times the quantity pm minus p squared all over m. And then I'm going to do my separation by multiplying by the reciprocal of this right here and multiplying both sides by dt. That gets me to m dp over pm minus p squared is equal to k dt. Okay. And now I'm going to want to integrate this. But in order to integrate it, first, what I need to do is I need to split this left-hand side up using partial fractions. This is m dp over the quantity p times the quantity m minus p is equal to k dt. And then that means I'm going to represent this as something over p plus something over m minus p. And I need to figure out what these constants a and b are. I'm going to just jot some scratch over here to the side. We've got a times the quantity m minus p plus b times p has to be equal to m. And so we've got negative a plus b has to be equal to 0 since there are no p's in that expression. And a has to be equal to 1 since an is equal to 1m. And so we get that a is equal to 1, and if a is equal to 1, b is also equal to 1. And so I'm going to go ahead and bring those back over here. There we go. Alright, now I'm just going to get rid of that scratch work because I might need this space later on in the development of my model here. Let's just erase all of that. Alright. Now that I've split those into partial fractions, now I can integrate both sides of this. I'm going to go ahead and integrate this. That's going to give me the natural log of the absolute value of p minus the natural log of the absolute value of m minus p. Why is it a minus? Well, it's a minus because when we take the derivative of natural log of m minus p, the derivative of that using the chain rule multiplies by negative 1, so we need to multiply by a negative to compensate for that fact. And the right-hand side is going to be kt plus a constant. Now, using logarithm rules, that gets me to natural log of p over m minus p is equal to kt plus c. And since population is not going to be a negative, nor is the carrying capacity minus the population going to be a negative, I'm just going to get rid of the absolute value signs here. Okay. Now, I'm going to raise both sides of this equation e to that power, which is going to leave me with p over m minus p on the left, and it's going to leave me with c e to the kt on the right. And now all I need to do is solve this for p, which sounds pretty easy, but gets a little ugly for us. The first thing I'm going to do is, in order to solve for p, is I'm going to take the reciprocal of both sides. So it gives me m minus p over p is equal to, and the reciprocal of ce to the kt is going to be ce to the negative kt, because the constant can move into the denominator and the exponent then just becomes the opposite of what it was. And doing a little bit of algebraic manipulation here, this becomes m over p minus 1 equals ce to the negative kt. I add 1 to both sides. And then I'm going to reciprocate again, p over m. Now I can't do, since I've got the 1 in there, I can't do what I did last time with the negating the exponent. This becomes 1 over 1 plus ce to the negative kt. Then I multiply both sides by m. P is equal to m over 1 plus ce to the negative kt. And there's our logistic growth model. Now we would want population to be equal to p sub 0 at time 0. And we can use that to figure out what our constant is. In this case, I don't know that that's going to be terribly informative for us if we let this be p of 0, because we don't know the initial population. P of 0 is equal to p at time 0. So p of 0 would just be m over 1 plus c, which isn't terribly informative for us here in the general form, but it's more informative for us when we actually have the population. And so right now what we have the logistic growth model, p equals m over 1 plus ce to the negative kt. And that's what we're going to use as our logistic growth model. Normally, though, when you see this written in text or on the internet or anything like that, instead of using c here, a lot of times I've seen a used as the constant. And so you'll see a model that looks a lot like that one. All right, and there's your logistic growth model. See you next time.